Listen, NASA and major observatories just changed the script on 3i Atlas. What started as a faint, fast visitor flagged by survey telescopes rapidly became a hefty headline-making object after deeper follow-ups, new imaging and calibrated photometry from the Vera C. Rubin Observatory, Hubble, and NASA teams pushed the nucleus size estimates well beyond the earliest guesses. That matters, and here's why size changes everything. A larger nucleus means more mass, more stored volatiles, and a different thermal response when the sun warms it. Models that assumed a tiny, quickly evaporating snowball now look inadequate. Larger equals brighter and slower to fade, which gives astronomers more time, more photons, and a better shot at solid science. But it also raises stakes. The bigger the core, the more interesting its chemistry and structure become, and the harder it is to explain odd behavior like limited tail formation or unexpected emissions. How did scientists get this right? Early surveys are discovery tools. They find moving lights and estimate brightness. Precision needs Hubble-class resolution, and Rubin's deep, well-calibrated imaging combine optical and infrared data, apply realistic albedos and coma corrections, and the brightness converts into a much larger physical core. That's what triggered the revision. Independent teams cross-checked images, subtracted coma brightness, and converged on a larger diameter than first thought. That's the scientific chain. Better data, better modeling, new conclusions. For you watching, this is not alarmist hype. It's a scientific upgrade. It means 3i Atlas will be a richer subject for spectroscopy, astrometry, and debate. Expect revised orbit and activity models, more targeted telescope time, and a flurry of new papers. The simple fact, we re-observing the biggest interstellar visitor yet, and the size change reshapes everything we'll learn next. Part 2. How observatories proved it's bigger. Techniques that change the numbers. Okay, let's be clear on the method. This isn't guesswork. It's a series of concrete measurements that force the community to revise the object, ES, size upward. First step, separate nucleus light from coma light. Comets glow because dust and gas reflect sunlight as well as emit it. Early brightness overestimates the solid core. High-resolution imaging from Hubble and the Rubin Observatory allowed teams to isolate the core S contribution and correct for the surrounding dust glow. Next, use multi-wavelength photometry. Optical gives reflected light. Infrared gives emitted heat. Together they tell you how much light is reflected versus re-radiated, which constrains albedo and diameter. That combination is what turned maybe a few kilometers into several kilometers for many teams. In short, better filters plus better calibration plus better subtraction of the coma is a larger, more robust size estimate. There's more. Simultaneous detections of water and hydroxyl emission at surprisingly large distances from the sun pushed scientists to reconsider surface and subsurface properties. If substantial water is coming off, but the dust halo remains compact, the simplest explanation is a big cold nucleus with localized vents rather than a small, uniformly active rock. Mars-based observations, rare close-angle views from orbiters, and Perseverance S navcam added geometry that helped constrain shape and brightness from another line of sight. All lines pointed the same way. Revise the size and revise planning. For you, this is how real science works. Iterative, conservative, and data-driven. New telescopes, cross-checked datasets, and multi-wavelength campaigns turned early uncertainty into a stronger conclusion. 3i Atlas is far larger than first estimated, and that changes the questions we now ask about its origin, structure, and future behavior. Pay attention. This is the part that makes chemists and cosmologists sit up. Multiple observatories reported a clear signal. Water vapor and hydroxyl emissions coming from 3i Atlas. At the same time, repeated spectral scans show a surprising lack of iron lines where we'd normally expect them. That combination is not a small footnote. It's a fingerprint that screams different origins. Here's why it matters. Typical comets in our solar system carry a mix: water ice, organics, silicate dust, and measurable trace metals like iron and nickel from the primordial materials that built planets. Finding abundant water, but almost no iron, suggests Atlas either formed in a protoplanetary disk with a very different chemical evolution, or it comes from a region and era of the galaxy where heavy element enrichment lagged. In plain terms, Atlas could be a snapshot of decades or even billions earlier chemistry. Spectroscopy is how we read that snapshot. Teams used optical and near-infrared spectrometers to identify emission bands of H2O, OH, and simple organics. They also scanned for forbidden lines and metal signatures. Iron wo absence isn't T because we didn't TT look. It was because the lines are weak or absent across multiple instruments and nights. That consistency across independent data sets is what pushes this from odd to significant. There are plausible natural explanations, but each raises its own questions. Maybe Atlas is a fragment from a system where giant planets formed early and swept iron into cores, leaving icy outer bodies iron poor, or perhaps cosmic ray processing over billions of years chemically altered the surface layers, masking metal signatures. Another possibility: Atlas's outer shell is coated in carbon-rich material, hiding spectral fingerprints until deep penetrating observations are possible. For you, this is where the science becomes a detective story. Water means volatile reservoirs survived billions of years, remarkable on its own. The iron gap forces rethinking of formation environments and galactic chemical timelines. Either way, Atlas isn't a run-of-the-mill comet. It's a messenger from a different chemistry chapter of our galaxy. If you've seen the Mars images of 3I Atlas, you already know why they shocked the community. A glowing, elongated object drifting across the Martian sky. No tail, no debris plume, no signature of a typical comet, just structure. Even experienced astronomers called it unnerving. Here's what really happened. The Perseverance rover's navcam captured hundreds of images of Atlas over a 10-minute window. Those raw frames were stacked by image processing algorithms to boost signal-to-noise. But as Harvard astrophysicist Avi Loeb pointed out, stacking moving targets can create artificial elongation, a blur that looks like a cylinder that explains some of the structure, but not all of it. Because here's the problem. Even with unstacked frames and parallel data from Mars orbiters, no visible tail appears. Not even a faint one. That's not a software glitch, that's physics. Every known comet generates a tail hundreds of thousands of kilometers long when solar radiation pushes dust and gas outward. Yet Atlas defies that rule. A near-perfect point source surrounded by a faint halo. NASA CWAS infrared spectrometers confirm water vapor activity, meaning sublimation is happening. But it's so localized that it doesn't spread into a tail. That's almost impossible under normal conditions. One theory says Atlas is coated with a carbonized crust, hardened by billions of years of cosmic rays. It vents through microcracks instead of erupting jets, keeping dust trapped under the surface. Another theory? The comet's rotation axis might be aligned directly with the sun, meaning its venting trails are hidden from view, a cosmic optical illusion. Still, many find the symmetry disturbing. It's too uniform, too stable, too deliberate, and because multiple instruments, on Earth, in orbit, and on Mars, confirm the same thing, this isn't just a visual quirk. Atlas has rewritten the definition of a comet. It's not behaving like ice and dust. It's behaving like something we haven't modeled yet. Professor Brian Cox finally weighed in on the mystery, and what he said reframed everything we thought we knew. Speaking in a BBC interview, Cox called 3I Atlas a relic of cosmic memory, older than our Sun, older than Earth, and untouched by time. In other words, Atlas didn't form here. It didn't even form in this solar neighborhood. Cox's team and other astrophysicists believe Atlas originated in a protostellar system roughly 7 to 7.5 billion years ago, nearly 3 billion years before our Sun was born. That would make it a survivor from a star system that has long since died or scattered its debris into interstellar space. This theory fits its composition: high in primordial water ice, almost no heavy metals like iron, and low overall density. The hallmark of ancient pre-solar material simulations show that during early galactic evolution, close stellar encounters could eject small icy bodies like Atlas from their home systems. Once free, they'd wander interstellar space indefinitely, frozen solid, until gravity from a massive star, like our Sun, finally pulls them in for a brief pass. That's exactly what's happening now. After 75 billion years in the void, Atlas has entered the solar system for the first and probably last time. Cox emphasized that it's not just a comet, it's a time capsule. A preserved sample of pre-solar chemistry, carrying molecules that existed before planets, oceans, or even carbon-based life. He explained that studying Atlas could reveal what the galaxy looked like before the Sun ignited. If we can decode its composition, Cox said, we're effectively holding the building blocks of every star system, including ours. That's why NASA, ESA, and multiple observatories are racing to collect data before Atlas fades back into deep space. Every pixel, every spectrum, every reading from this object is a piece of the universe's earliest autobiography, and it's drifting right past us. Once in eternity, how Atlas escaped its home star system. Imagine a silent explosion, not a blast of fire, but gravity itself snapping a solar system apart. That's likely how 3I Atlas began its 7.5 billion year odyssey. According to astrophysicists, comets like Atlas are born in the cold outer disks of star systems, far beyond the warmth of any sun. They're built from leftover ice and dust, the raw remains of planetary creation, but sometimes chaos wins. A nearby stellar encounter, a supernova shockwave, or even the gravitational pull of a passing giant planet can sling a comet out of its system entirely. That's what researchers think happened to Atlas. Somewhere in a long-dead system, a star either collapsed or migrated too close to a stellar neighbor. The gravitational tug-of-war threw Atlas out, fast enough to escape its sun's gravity, but too small to be captured by another star. From that moment, it became a galactic wanderer. For billions of years, it drifted through interstellar space, through nebulae, radiation storms, and the chaos of the Milky Way. No collisions, no sunlight, just eternal darkness and frozen silence. Until by chance it crossed paths with the solar system's outer gravitational field. NASA's orbital reconstructions show Atlas's trajectory is hyperbolic, not elliptical, proof that it came from beyond. Unlike any periodic comet, it won't return. It's passing through once, then gone forever. Professor Brian Cox called it a ghost from before the sun. That phrase fits perfectly, because what we're seeing right now isn't just another rock in the sky. It's evidence that our solar system isn't unique, that planets and comets form, evolve, and scatter across the galaxy all the time. And every so often one of them, like Atlas, drifts into our cosmic neighborhood, offering a fleeting look at a star system that no longer exists. 5 billion years through the galaxy, a survivor's story. Now think about this. 3I Atlas has been traveling longer than our sun has been alive. That's not exaggeration. That's astrophysical fact. The Milky Way rotates once every 230 million years. Atlas has likely completed over 30 full galactic orbits circling the center of our galaxy before finally crossing our path. That's 7.5 billion years, older than the Earth, the Sun, and almost everything we've ever studied up close. So how did it survive? Space isn't empty. It's filled with radiation, dust, plasma waves, and high-velocity debris that would erode most bodies over time. But Atlas endured. Scientists believe it's coated with a carbonized crust, hardened by eons of cosmic rays, like a natural armor. Beneath that black shell lies pristine, frozen water ice, the same ancient material that existed before any star lit up. When it finally entered the solar system, that ancient surface began to whisper, not explode, not vent violently, just faintly release traces of vapor. That's how astronomers detected it. That small signature of water gave it away, after billions of years of silence. Researchers estimate only about 8% of the surface is currently active. The rest? Dormant, sealed off by radiation chemistry. That's why it doesn't behave like typical comets. No grand tail, no chaos, just quiet endurance. Its path through the galaxy is a cosmic miracle. It's been through supernova shockwaves, passed near black hole gravity wells, and yet remains intact. That is not just luck. It is a window into how robust early interstellar matter can be. NASA scientists now call it a frozen time capsule of the early universe. And the deeper we study it, the more we realize that this comet isn't just an object. It is a survivor of creation itself. It's proof that the universe keeps its memories, even after 7 to 5 billion years of darkness. Breaking the rules, Atlas versus every known comet. By now, one thing is clear. 3I Atlas isn't following any rule in the Comet Handbook. Every model says comets develop tails, shed dust, brighten with solar heat, and fade after perihelion. Atlas does none of that. As it passed Mars's orbit, astronomers expected a typical outburst, a visible jet or flare-up instead. Nothing. Its activity remained flat. No fragmentation, no debris plume, no brightening. That's like watching a campfire that refuses to burn, even with oxygen and flame. So scientists are rethinking what defines a comet. Atlas might not be a comet in the classical sense at all. It could be what researchers call a devolatilized core, the fossil of a comet that exhausted its ices billions of years ago. Its shell, likely thick with carbon compounds and silicates, has locked away every volatile molecule inside. When sunlight hits, only a whisper of vapor escapes through microscopic cracks. That's why its tail never forms. It's not lazy. It's ancient. But that's not the only anomaly. Its rotation is perfectly stable. Most comets spin irregularly as jets of vapor push them off balance. Atlas's spin rate? Constant, no tumbling, no wobble. Even its light curve, the brightness over time, is smooth like a solid object rather than a porous ice rock. Astrophysicist Brian Cox explained it best. It's not that Atlas breaks physics, it's that our models were never designed for something this old. Atlas has effectively become the first object to challenge how we classify cosmic wanderers. It's forcing astronomers to admit that not everything in space fits neatly into categories: comet, asteroid, or rock. Sometimes what drifts into our skies is older than those definitions themselves.